Alright, here we are, back for another day of AVL trees, and maybe we'll do Splay trees and then some other things. Let's see here. Cool. Yes, well, not a nullifier. Not a nullifier. I was just saying that 0 didn't matter. Either you pick it as the base case, or pick 1. It's fine. Right? It really, like, that's, I mean, I explained it on, yeah, I don't, it really doesn't matter what your base case is because, as I said on the Discord, if you pick 0, then you end up with like nothing on one side. Yeah, you're over analyzing that side of the formula, right? Like that side of the formula, it goes from 1 squared or 1, like 1 squared plus 3 squared plus dot 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 up to 2, I think 2n minus 1 squared. But the implication is that 2n minus 1 is bigger than or equal to 1, right? So if 2n minus 1 is equal to minus 1, then no, right? Like it's going up, right? So you're like too strictly applying that formula. So just pick, if you insist on that, then yeah, pick 1 as your base case. I'm telling you, just pick 1 as the base case, right? Like if that formula is confusing you, then it's too much, right? You're thinking too hard about it. Okay. Okay, and then, yeah, so, okay, let's get back into AVL trees. And I might talk a little bit about 1b, I think, maybe, like the induction problem. So, yeah, so let's talk about AVL trees, right? Basically, AVL trees are binary search trees. So that means that for any node, so if the value here is v, and you're trying to insert or delete a node or find a node, right? If the thing is less than v, it goes into the left subtree, and if it's greater than v, it goes into the right subtree. And that's, so basically, and that applies to all the children. So for instance, if there's something like this, you come to any node. If, for instance, this is 10, this is 5, this is 8, this is 2, 13, 11, then if you're trying to put, let's say, 9, I guess, inserting 9, then it doesn't matter if this tree is AVL or not, right? Currently, this tree is an AVL structure. The reason why it's an AVL structure is because if you count the heights here, let's count the heights like the book does. I think it starts off all the nodes here at height 1. These are height 2, and this is height 3. And so how do you tell if it's an AVL structure? You tell it's an AVL structure because, remember, the height of the left child is equal to, or I should say, really, the height, well, I'll say this, the right child, plus or minus 1 or 0, right? So it could be either 1 or 0. It could be equal, so it could be truly equal, whoops. Oh, cool. Yeah. So, okay. And then, so basically here they're equal. Here, technically, this is so since this is not in the tree, this is height 0, so this is still AVL though, because it's okay to have something of height 1 and height 0, right? This is a leaf, like a null leaf or something, whatever you want to call it. So, you know, you might think that rebalancing operations are complicated, and the answer is really there's only really 2 operations that are used in rebalancing. And that would be rotate left, whoa, and rotate right. So in a sense, there's actually somewhere between 1 and 2 operations, right? And so it's really the same operation both times. So before I get back into maybe coding or maybe some kind of theory about this, well, actually, let's talk about the rotation operations again. So, for instance, here, let's say that we have something like this, where the parent. Actually, I like this. We're going to start with the node we care about in black, and then we're going to have the parent in purple because purple starts with parent. Parent starts with P. And then green for the grandparent, because grandparent starts with G. And so here's one situation that you can find yourself in. Let's get rid of this red node. I don't know what R stands for. So keep in mind that all of these nodes can have, let's call them subtrees, basically. They can all have trees coming off of them on the other sides. And so let's talk about what happens. Basically, the idea is if you end up with something like this, and you know that, for instance, this has height, let's say that this has height h plus 2, and this just has height h, okay? Right? So let's assume this. So this is the node we care about. This is the parent, and this is the grandparent of that node. And so here's all of their constituent subtrees. Let's label them just to make sure that, because I don't have enough colors to label them all, let's just call this one alpha, beta, gamma, and delta. So the good news is that the vast majority of these are not going to move. And you kind of see what we want to do here, right? The goal is that we are going to put the parent on top, right? And we're going to shift the grandparent to being the right child. And we're actually going to keep the relation. So we're going to keep the relation between the parent and the child. This doesn't, right? So this link stays, right? This stays. This one gets shifted. And then let's redraw some of these trees. So alpha and beta. So here's alpha and here's beta. They don't get moved, right? So you can kind of ignore them. As long as you don't touch those pointers, you're fine. And then the grandparent has a right subtree of delta, right? And that stays as well. And so the good news for us is that when you're looking at this operation, we would call this the rotate, right? I guess we would call this rotate right. I always have to check on my hands. I have to be like left, right, left, right. This one's right. And you see the only problem, right? What's the real problem here? The problem is that if you notice, you know, what happened to gamma, right? That's the only real obstruction here, right? And so gamma is kind of orphaned now, right? Orphaned. But think about it this way, right? everything in gamma, right? An element, well, let's not call it epsilon, let's call it an element E that's in the subtree gamma. E is bigger than the value at P, right? Or bigger than or equal to, technically. So the thing is that it goes into the, if P is the ultimate root of this subtree, right? Yeah, so basically, you notice that once we break this relation, so this is the relation that we're breaking, can we just stick this here, right? I know that I'm kind of going too slowly through this, and you've already predicted it, so you're ahead of me. But this is what we want. But is this okay, right? I mean, so G has a free left child now, right? Because G's left child used to be P, the parent. Is it okay if we just glom on, basically transplant or prune or whatever you want to call, anti-prune this tree to put gamma back in here? Well, the good news is that anything in this subtree here has to be less than the value at G, right? That's the thing that keeps everything safe, is that everything in this, every E in this subtree gamma has to be between, it has to be bigger than or equal to P, and it has to be less than G, right? Because, and so we notice that things that are bigger than P are going to go this way, things that are less than G are going to go this way. And so as it turns out, this is okay. Yes. And like when you kind of realize that, right, that should fill you with a certain degree of kind of satisfaction or maybe confidence, right? Because technically this is like case 1. There's like 4 different cases that you can run into. This is really just case 1. And so, like, once you figure out like this and you're pretty sure that case 1 is going to fix you, well, okay, so let me just say what case 1 is currently fixed. So currently what we know is that now rotation preserves the BST property. Well, here's the question. If this is of height h plus 2, right, then either this one is height h plus 1 or this gamma is height h plus 1. But let's assume that the problem is actually in this direction, not in this direction. So let's assume that gamma is of height less than or equal to n. So if gamma is of height less than or equal to n, and then, so this one is the height n plus 1 node, so this has a height of n plus 1. Now we put something which has height less than or equal to n plus 1, or less than or equal to n here. The height here, let's assume that the height here is h, which is, I'm just using n in this case, so the height is n. So if the height is n here, the height is less than or equal to n here, then the height of this grandparent is now n plus 1, right? We can reconstruct it. And so we went from having a height of h plus 2 or n plus 2. Let's actually just kind of delete the tops of these h's. So we have removed 1 from the height on this side, and we've added 1 to the height on this side. And so now we know that the total height of this subtree is n plus 2. So overall, what we've done is we've changed a height, technically it's a height n plus 3 subtree into a height n plus 2 subtree, but we've also rebalanced it so it's not so one side heavy. And so that's one of the cases. So, okay. And so notice that we always have to take the heavy side when we're considering these cases, so we cannot take the light side. How would we know how to determine the height? That's a good question. You determine the height as you're inserting into the tree. So the height is going to be equal to the max of, well, it's the left dot height, the right dot height, plus 1. So basically, this is the rule for determining height. And so you see that you can actually recalculate these as you insert. So as you go down the tree, you will insert as usual. So basically, when you have a binary search tree that's AVL, right? So what you're going to do is you're going to insert as usual. Like if you insert this new node, and then you're going to have to recalculate the heights on the way back up. So generally, you'll do this kind of thing recursively. And the reason why you're going to do this recursively is because you will you'll have to do the rebalancing on the way back up. So it's always nice to have the path that you trace back down the tree as you go back up the tree in the recursion stack. So recursion helps here. So unlike in a normal binary search tree that you can just use like a while loop and just insert on your way down and then not worry on the way back up, you actually do have to recalculate the heights on the way back up. So like here, the heights would be 1, 1, 2, 1, 3, and so this is currently AVL, but once you insert this one becomes height 2, so this guy becomes height 3, and so then this one actually becomes height 4. But the problem is, so the problem isn't here, right, because this is height 0. So there's no tree here, so this is up height 0. 0 and 1 are 1 different, so that's okay. 2 and 1 are 1 different, so that's okay. So when we're here and we check the heights of the right and the left subtrees, we're still okay. But then when we go back up to here, all the way up to the parent, then we see that there's a problem because the heights of these two don't agree. So then what you have to do is you actually have to trace your way back down on the heavy side. So, and the reason why you have to do that is because of the deletion operator. So the steps are like 1, insert into the binary recursively. And then 2, what you're going to do is update the heights on the way out. And then if unbalanced, then do the rebalancing. And so the question is, if you notice that this is the heavy side, like what exactly are we going to do to fix this? And so the answer is, since this is not a straight line pattern, this is one of the weird like left-right or right-left. So that in this case it's a left-right thing. We actually have to do 2 rotations. And let me remind you of how to do those rotations. So for instance, let's say that we have something where we have okay, let's use the colors again. I think the colors are helpful. Because it's really hard in the book to keep track, and this is really true in most books. They don't really draw it out like this, and so they are just like, oh yeah, so obviously you'll figure out all the relations, and so let's call this the new node n, and let's use I don't know, let's use blue, since blue is better than red, I think, for all the subtrees. So in order to balance this, and let's say that the heights are as such, so the heights here are going to be, this is going to be of height h plus 2 here, and this is going to be height h plus 1, and then I guess these are height h's, right? Every one of these subtrees is height h, and then of course this one's height h plus 3, but we don't really have to care about that. So, so now let's label all the trees, give them Greek names, alpha, beta, gamma, and I don't know, xi. And so, okay, cool. So with this one, this is like, we'll call this case 2, And we see that it's different from case 1. In case 1, you notice that the tree descended in the same direction. But here, for case 2, we have this left-right thing. So I'll call case 2 the left-right case. So case 1 is left-left, case 2 is left-right, case 3 will be, I guess, right-left, and then case 4 will be right-right. So, and the good news is that the 4 cases are symmetric, right? So case 1 and case 4 are basically the same, and case 2 and case 3 are the same. It just flipped, right? Symmetric, if you just, I guess, flip them. And of course I've just written under my head, so don't write here. Yeah, I can make these available. So if I learned my lesson on this. If I give the actual link to the live board, then everyone can edit. There's no like watcher permission. So as you pass up through the parent, you update the heights, yes. So in this case, what you're going to have to do to rebalance is you rotate this way first. And so what we get in that case is this. Let's try to draw it. So you'll get grandparent, node, parent. So the parent is sitting down here, the node is sitting here, the grandparent doesn't move, okay? Is there any way to export them? Yeah, I can export them, so yeah, I can do that. This is also, I mean, technically this is done in the book, but I will try to make these slides available because I think actually what I'm doing here is, it's not actually the worst, so you can kind of read this stuff. So this is alpha, this will become beta, and this one got moved, right? This one was transplanted. So then the gamma subtree is here, and then the C subtree is here. Yeah, update the height the same way. Again, everything uses this formula, right? This formula. Because I promise you that what's going to happen is, and kind of what you assume, is that all the heights under you are correct. By the time you get up to wherever you are, you assume that those heights are correct, and so those heights aren't going to change anymore. Or I guess at least until you do a rotation, at which point you do have to update the heights again. So okay, so this one now has, I guess, this one only has height h plus 1 now because of this. All the subtrees have height h, so then now this has height h plus 2, and this has height h plus 3, and actually now we're back in case 1. So basically what you do in one of these alternating cases is you actually reduce this into a case 1, and you'll actually reduce case 3 into a, well, yeah, you'll reduce case 2 into a case 1, you'll reduce case 3 into a case 4. And so everything eventually becomes a straight line rotation. And so this is the first step. And then the second step is here, where now we rotate the other direction around this node. And so we'll end up with the node on top, the grandparent. I mean, this is, I promise you all of this is actually specified in the book, so you don't actually need any of these slides, but I will try to give you these slides because I think they're... And then, of course, here, hopefully, and then we have to transplant gamma again, and then, there we go. And so now, if we look at all the heights, remember all these blue trees all have height h in our imagination. So if they all have height h, then these have height h plus 1, this is height h plus 1, and then this has height h plus 2, and everything is fixed. Right? And so after you're done with the rebalancing, at that point you have to update the heights again. And then, of course, let's talk, case 3. Case 3 is when you have grandparent, parent, node, but now it's the other way, right? And so then the first thing that you do is you convert it into grandparent, node, parent on the now parent. So that's the whole point, is that the old parent is now the right child. So and then you have to, so this is a rotation this way here. So you rotate left, or no, I'm sorry, you rotate right. And then you see that this is still kind of unbalanced, so now you rotate. And so the final operation, so this is step 1, and then step 2 is that you end up with the node on the top, the parent, and now the grandparent. And remember, now they're all kind of children. So let's draw in the subtree. So this is alpha, this will be beta, gamma, and delta. And so alpha doesn't move here, alpha stays. Beta stays. Gamma needs to be transplanted, so gamma gets transplanted here. And then finally, when we rotate back, gamma and delta stay, and we have to transplant beta. So beta gets transplanted, alpha stays as, so alpha never moves, right? Alpha never moves, delta never moves, but these two both get transplanted. You see how, in order to make n, no. So you're not actually, I promise, so you're never breaking, right? You're never actually breaking, like the grandparent, like dot left, right? Grandparent dot left is equal to alpha, and it's always alpha. So this rebalancing only occurs with the leaves. No, because you see here, these are not leaves, right? These have subtrees at every point, right? These all have subtrees. Sometimes books don't draw them, and I didn't draw it initially when we did all the rotations, but you see that every single one of these has subtrees. So parent dot right is always equal to delta, and actually that never gets modified, right? This whole thing, during all of this stuff, nothing ever changes. And then, of course, basically, in the end, g dot right ends up getting set to be n dot left, and p dot left gets set to n dot right. Anyway, let's go over the last case before we get into more concrete things like coding. So case 4 is basically the reflection of case 1. So case 4 is where you have a grandparent, and then you have a parent, and then you have a node. And for this one, and I'll draw in all of the subtrees. basically, if this is height imbalance, so if this is like h plus 3, I guess this is h plus 2h, and this will be h plus 1. So it's not height imbalanced here, right? This is okay. The problem occurs here, right? This is where it's not height balanced because this differs by more than 2. So then you're going to be like, okay, well, since this is different by more than 2, then what you need to do, and the place where you detect it is you detect it up at G, right? So what you have to do is you have to trace back along the heavy side, and so then you start at the grandparent, and then you trace down through the parent and the node to get the heavy side of the tree. I almost said function. So you get the heavy side of the tree, and then what you see is that you're going to rotate around the parent, and you're going to rotate left. And so the resulting rotation is going to end up putting the parent on top. And then we're going to have the node stays. So the good news is that the node stays as the right child. The grandparent moves down to take the place here. And so then, and let's look at the trees that stay. So alpha stays where it is. Gamma and delta stay where they are, right? This one stays, this one stays, this one stays. The only one that gets transplanted is beta, because beta was on the left side of the parent, but now it's on the right side of the grandparent. So this is the only transplant. And so now if these are all height h, then these are height h plus 1, and this is height h plus 2. And so now this is all balanced, and so since it's balanced, you can then pop back up to its parent, right? You can go all the way up to its parent. Okay, so those are the 4 cases. And as it turns out, these cases, these rotations, are actually, like, you have to do some slight different stuff, but it doesn't matter if we're doing AVL trees, or we're doing Splay trees, which I'll talk about, or we're doing red-black trees. Yes, exactly. The nodes have to point to different trees, and I'll show you what. We'll get to coding. So I don't care whether we're doing AVL, Splay, or red-black. These are the only operations that you ever do on the tree. Now, with Splay trees and red-black trees, Splay trees you don't actually keep track of the heights. You just always splay up when you can. And red-black trees have red and black colors with different rules. But if you forget about the heights, right, and you pay attention to red-black, there are then rules about which case to execute. And so basically, we have gone through the only process that has ever really used to rebalance binary search trees. And you'll see that we use those, we use these 4 cases, we use these 4 rotation operations in every single rebalancing that we ever do. Okay, so I have to close Steam, I think, because I'm getting hammered. All right. Okay, sorry about that. All right. So this is pretty cool, right? Like, I just had a friend who he just sends me stuff, and he only messaged me like, I've told him my class times, and he only messages me during class. It was like when I started teaching at UMD, like, my parents, when I just started grad school, they would only ever call exactly when I started teaching class. Like, they would never call me at night. They would never call me, like, at a reasonable time. I would give them my schedule, and they would only ever call right as class was starting. And so if I ever forgot to silence my phone, I would always get a call right then. I don't know why I'm lucky. Okay, so what am I gonna do? I'm gonna put this here so that I can have my hands free to type stuff. So okay, let's do some implementing. Maybe this project is kind of full of stuff, so let's maybe make a new project. Let's call it, I guess, a console app, sure. Let's call it CMSC 341 AVL. Okay, here we are. Completely new project, right? Okay, so let's delete all this garbage. And so now let's create a new class. Let's create the AVL Tree class. The AVL Tree class needs well, that I cannot say. I have not seen I have not seen that yet. Yeah, so okay. And so let me just tell you what kind of pointers we need here. So we need a pointer p parent. Actually, let's be lazy and just call it parent so that I'm not doing p underscore all the time. Let's do a left pointer, and let's do a right pointer, and then we need an int height, and then we need an int, what other kind of int? Value. So let's write the constructor, value element, height 0, parent null pointer, left null pointer, right null pointer. So, okay, cool. Oh, semicolon. I was like, wait, I didn't make an error yet. You just wait, I'll make plenty of errors. But I haven't done it yet. Okay, so that is the structure of the node. So you might ask, do we need this parent pointer? Yes. This is regular BST stuff. Do we need the height, or could we just calculate it? Well, we need it. Unfortunately, if you recalculate it every time, are there edge cases if the grandparent is the root? Yes. And this time I'm actually going to do it correctly and not call it m head, p head. I'm going to call this p root. Because in a tree, there is a root, not a head. Right? Okay. So, and that's all you really need for an AVL tree. So what are we going to need, right? We're going to need a rotate right method. We're going to need a rotate left method. Because unfortunately, they are basically the same operation, but they're not quite the same. Like, everything is symmetric. Right and left are flipped. So you can't just reuse the same code. I wish you could, but you can't. So what kind of stuff does an AVL tree have? It has an insert function. Well, so not rotate right and left, okay? Because rotate right and left is going to take an AVL tree node pointer. And these two functions, we don't want them to be accessible from the outside of the class. Insert, definitely accessible. Remove, definitely accessible. And, oh, I guess delete's a keyword, right? There we go. technically we might want a copy constructor, but I'm not sure that I'm going to actually implement this in class. Mainly because that's just kind of a waste of time. There should also be a destructor, which I'm also not really going to bother with. Yeah, I guess we do kind of want a like dump. Well, so the thing about printing is, yeah. So let's just do an in-order traversal of the tree once we are done with it, and we can kind of anyway, we can kind of deal with that there. Okay, so this is like print. Okay, so I think, all right. Okay, so if we want to rotate, we have to decide how the node is going to be passed, but let's implement the rotations. Whoops. Come on. Oh, sorry. There we go. So this is like the meat of the code. This is the stuff that does everything. So how are we going to make this rotation work? So when we rotate right, and remember what our perspective is. So our perspective, I think, is going to be that of the parent. So for instance, if we're going to rotate right, let's look at case 1 for the right rotation. So if we're going to rotate right and we're rotating, let's say that our fulcrum is here. So this is where we rotate around. So this is the node that we're talking about here. Okay? And so if we're going to rotate this right, then what happens? Right? And so we have to list out all the different things that happen. Right? So basically, if we're going to rotate right, we see that the grandparent dot left becomes the parent dot, becomes this, this is the node we're rotating around, the parent dot right. So we can have AVL tree node pointer grandparent is equal to node parent, right? And so we might want to keep track of that. I'm not 100% sure. I'm just doing this on the fly. So, yeah, so basically then what we want to do is we want to make, right, we want to push this over to here. So the parent dot left is unaffected. I'm sorry, the node dot left is unaffected. And so basically we need the grandparent arrow left is equal to the node arrow right. But if we just do it this way, then we might have just erased the left. Have we just erased the left thing? Well, yes, we have, but remember that the left thing pointed to, so grandparent arrow left pointed to node, right? So, so it's okay. This is going to not screw us up. Okay, but what is this doing? This is transplanting the tree. And so here we also need to reset the node arrow right arrow parent is now not node anymore, it's now grandparent. Right, because everybody has a parent node. And so the only thing left to do is basically to say that grandparent parent, well, okay, so the node arrow parent is equal to grandparent arrow parent. And the reason why is because node becomes the top, grandparent becomes the, I guess, what? Let's look at it here. It becomes the right child of node. So what that means is that node arrow right is equal to grandparent. And I think that completes it, right? Because grandparent arrow left is node arrow right. We've transplanted the tree. We have reset the parent of the subtree, right? This resets the parent of the subtree. Because the node became the top, the grandparent becomes the right child of the node. So node arrow right is equal to grandparent. And then we have to reset because now the node is on top. So the grandparent's parent, or great grandparent, becomes the parent of the node. And then I think the only thing left is to update the grandparent's parent, like that. Now, this is not correct in one way. So remember now that the grandparent is sitting on the right side. The parent, the old parent is now on top, and the node has been shifted up. So basically this does it. The only case that this doesn't track is the case where, like, what if you know, because if the grandparent is the root node, so basically if we do this regardless. Oh wait, we have to do this at the end. So what if grandparent is equal to root node? And so the answer to this is that well, what happens? So if the grandparent arrow parent, then we know that it's not the root. But if it is the root, so this is basically grandparent is the root. So what now? So the answer is that the parent, the old parent, becomes, right? Because if you notice what's happening here, the old parent in purple is moving up to the top. So if this is the root, if G is the root of the tree, then actually we need to update the root of the tree to be P. So P root is equal to Yep. Cool. And now, so this ends the, so basically, really all we've done here is we've shifted this node up. So we have to think of all the things that are happening, right? Let me see if I can kind of do this then. So what's going on, right? The grandparents left becomes the parents right, and so node in this case is equal to parent, right? So the only thing to keep track of here is that node is actually equal to parent here. I think it's probably the easiest way to keep track. So so the grandparents left becomes this gamma here. Let's push that in. There we go. Yep, so you see how the grandparents left becomes here, and now what we're doing here is node.right is still pointing to this gamma, and so we can use that to point back to gamma's parent and tell it to point up to the grandparent. So really this is the transplant operation. This transplants the tree onto the grandparents left, and then what happens to the parent.right becomes grandparent, but now we cannot update yet because remember, grandparent's parent is pointing off somewhere, right, to something else. Either it's null pointer or it's the root. So if it does point to something else, then we set the node's parent, right, purple's parent, to be the grandparent's parent. And so that is how we do that. And so that's if it is not the root. But if it is the root, if grandparent does not have a parent, then we just set the root node to be equal to P, the purple node, right? Because node is the purple here. And then finally, we get to update the grandparent's parent to just be the node. So really, these are only two operations. Like the only two things we're really doing is grandparents.left is equal to node.right, and we're doing node.right is equal to grandparent. But we still have to fix up the parent's parent because it's still linked somewhere. It's either linked here or it's linked here, and it's hard to say how it's linked. And then, yeah. Okay. So that is the code for rotate right. And so the good news is that rotate left is basically the same thing, copy paste, except in this case you're going to, like, I'm going to say this, and I don't know if, maybe I'm just terrible at this, or maybe this is just a fundamental fact about the way that this works, is that, like, if you just read the code, it's very, very difficult to understand, right? It's extremely difficult to be like, I understand what's going on here. Even with all these comments, right, it's still difficult. Where is line 41 on the picture? Node.left is equal to grandparent. So that would be, I guess, in case, if we go down to case 4, let's see if we can go to case 4. So in case 4, for the rotate left, so this is rotating, oh wait, whoops, it's rotating this way, so it's rotating left. Let's see, node.left, so p.left is equal to the grandparent, right? So yeah, so you see here, you have the grandparent, the parent, which is our node, and the thing I'm calling n, which let's just call it n from now on. So node, which is actually the parent, dot left has to become the grandparent here in case 4. And so that's why that's there. Basically, what I suggest you do, I mean, honestly, one way to do it is to literally just cut out pieces of paper and like color them and name them, and then just do the operation with those cutouts, and then like just see which things you have to relink. Okay, like there's nothing special going on in any of this code. It's literally just I'm taking this shape of the tree and I'm making it into this shape of the tree, and I'm just doing everything necessary to relink everything so that nothing, like beta isn't orphaned, the grandparents, like G purple.parent is green. You know, maybe we could even, maybe that's one way to do it. We could even just change this to, this is green, right? So now node is now green. We could even, actually I kind of like that idea. Maybe I'll even change that so that instead of calling it grandparent, I'll call it purple. I'll call node equal to green, and then if I ever actually hit anything with, so you notice that the actual node call n never gets touched. So actually all we need is purple and green. So for instance, this is green, grandparent is purple, purple is green.parent, purple.right is green.left, purple, green, green, purple, right? I don't want to find replace because it's gonna screw up the other function too. There we go. I think I kind of might have done it right. Who knows? So, okay. So at this point, I think what we should do, and what we have to add to all this code, is that we need to fix up the heights again. So this isn't part of the rotation. So we can't really test this yet because we don't have any of the other tree structure stuff done. So yeah, this isn't part of the rotation. Yeah, I know I don't use all the compiler features. I tend to, I'm very bad about that. So this isn't part of the rotation. This is fixing up heights, right? And so what you have to do now is you have to remember whose height needs to be fixed, right? So basically, G's height needs to be fixed. So purple is going to be, purple.height is going to be equal to 1 plus the max, and we'll just implement max, I guess. What's wrong with you? Oh, it wants me to implement max. I'm not terribly happy with the person that's leaf blowing, weed whacking, whatever. So return I guess if A bigger than B, return A, else return B. There are definitely better ways to do this, but I don't care. I'm sure you can use a ternary operator, like, return A bigger than B, A, B. There. I used a ternary operator. Done. Okay. Okay, cool. So basically, oh, it's fixing that for me. That's fun. Something like this. Oh, no, I'm confused. What's wrong with you? Expression must have a class type. Oh, because it's... Okay, cool. There we go. I mean, the only problem is that... Oh. There we go. Fixed. Okay. So, we fix purple, and then we'll fix green. And there we go. So that fixes the heights. This also has a bug in it, unfortunately, so maybe actually we'll rewrite max to take, instead of heights, we'll take AVL tree nodes A and AVL tree node B. And the reason why we're going to do that is because we can kind of fix things in a tricky way. We can kind of be like this. If A, right, basically if A is not equal to null pointer, and B is not equal to null pointer, then return A, else if A is not equal to null pointer, return A arrow height. Else if B is not equal to null pointer, return B height, else return 0. So unfortunately, this code has to be done somewhere, so maybe this is just an easy way to do it. Because unfortunately, if you try to access these heights, and that's the problem here, is if you try to access, we know purple and green exist, but we don't actually know if purple arrow left and purple arrow right and green arrow left and green arrow right. Sometimes they may not exist, and if they don't exist, then we're going to get null, I was going to say null pointer exceptions, but basically seg faults. I think it's fine. Right? If A is not null pointer, if B is not null pointer, I think. I'm pretty sure. 80%. I give it 80% certainty. Okay, so this is cool. We get to fix up the heights. So hopefully that means that we don't have to be fixing up the heights as we go in the insert function. So, okay. I keep clicking on this. Let's kill that off so that I don't click on that anymore. All right. I mean, I could easily be wrong about stuff because I make basically countless, endless mistakes all the time. Cool. And so insertion, we're going to do nothing here, right? So this is not working. But how do we deal with insert? So AVL tree. Okay, so how do we do this? What do we want to do? Good question, good question. So we want to insert, basically we want an insert helper. And let me show you why we want an insert helper. So we want the insert helper because we're going to need a node pointer as we go up and down. So so basically we're just going to call insert helper on value queued. Okay? And so so insert is boring. Insert helper is actually where everything's going to be done. Interesting. So, okay. I guess actually we can do a slight bit of insertion. So if not proot, right? So if proot is truly null, then we can just say proot is equal to, you capitalize, AVL tree node, value, right? Because a single node is pretty balanced, so no worries. Oh, you know what? I think I made a slight mistake in this. The default height should be 1. Any non-null node needs a height of 1, not 0. I just remembered that. Okay, but anyway, now that's all fixed. So, and remember, it's going to set the parent to null. It's going to set the left and right children to null. So, so we're done here, right? This is all we need. So else, then we do this, right? Because we don't want to do insert helper if the root is null. So, okay. So basically, we're going to insert as usual in a BST. So if value is less than node, well, first, I guess, should we check if node is not null? I guess we're going to assume node is not null. Dangerous assumption. That's segfault time, right? If value is less than node.value, we're going to call insert helper on. Well, I guess if node.left, then we'll call insert helper on value node arrow left. And that's cool. Else we can insert at that position. We'll insert there, so that means that node arrow left is equal to a new AVL tree node with the value of value. Cool. And then we have to fix some stuff, right? Because now node arrow left arrow parent has to be set to node, right? So this is a new feature in AVL trees and in trees where we track parents. Okay. Okay, cool. And so now elif the value is bigger than or equal to node. I guess really this is the else case, right? Then we copy paste. And we do node.write, node right, node right, node right. So this is the insertion completed, right? The insertion is actually all done here. So now we need to do the fix-up. So, yep, so now what we're going to do is we're going to assume, right, that we've either created the node or we've popped out of one of these insert helpers, right? And so what that means is that the tree under us is balanced. So we're going to assume that the tree under us is balanced. We just need to balance the tree at our current position. Right, so what we're going to do is we're going to check if well, I guess we can check if node left and node arrow right and I guess node arrow left arrow height well, it's hard to really. What I want to do is use the absolute value of node arrow left arrow height and node arrow right arrow height. It's bigger than or equal to 1. No, bigger than 1. Sorry, bigger than 1. We could include math, I guess, right? Does that have absolute value in it? Hopefully that has absolute value in it. Well, the red goes away. Cool. So if this is the case, then we have to do some rotations, right? And so because remember here, if the difference in the heights is equal to 1 or 0, then it's okay. But if the absolute value, right, if the difference in the absolute value is bigger than 1, then we know that it's 2 or bigger, so then we have to do something. So else if node arrow left and node arrow left arrow height is, I guess, so now we're assuming that the right doesn't have something, so if the height is bigger than 1, then we'll have to do a rotation. The cool thing is that here all we have to do in this case, I think, is just rotate. So if the left is heavy, we rotate right on the node, and that should fix it. Why is that angry? Oh, because I haven't made this an AVL tree method. And then here we can rotate left on the node. And then else, what that means, we do nothing, right? So there's no else. If none of the children, right, are non-null, then we don't need any rotations here. We're at a leaf node. So really, else is nothing. So here is where we have to implement all of our cases, right? So unfortunately here, what we need to do is we need to trace down the tree to find the side with the max height. So what we need to do is, so basically, in this case, purple is equal to node, right? So what we're gonna do, and I know this is, you don't need to do this, but I'm doing it for clarity. So then what we do is we pick the max side. So if purple arrow left and purple arrow right, oh wait, we already know that's true, so it's definitely true. So we pick absolute, ABS is just absolute value, right? Right, standard as expected absolute value. So yeah, basically what we're doing here, so basically remember that if you take the absolute value of x minus y and you ask when is that bigger than 1, then the absolute value of x minus y is bigger than 1 when x minus y is bigger than 1, or when y minus x is bigger than 1, which is what we want, right? Because when one of the heights is bigger than the other height by more than 1, so really what we're looking for is like this. So let me just say that this is probably why they're not going to have you implement an AVL tree in your project. It hasn't really been done in at least a few years, because you see that it's not terribly easy, right? So now we need to find green. So let's find green. The green node is the maximum of the two heights. So basically we're going to take if purple arrow left arrow height is bigger than purple arrow right arrow height, then green is equal to, and let's just create the node green equals null pointer right now, green is equal to purple arrow left, else green is equal to purple arrow right. Okay, so then we need to find the next direction. So now we need to find the direction of the maximum heights, and so now we need to find the black node. So some books will make this into a helper function, but actually this is, when you do it all together, it's kind of better. It's just a gigantic blob of code, though. It's really enormous, right? So let me see here. What am I doing? Okay, so we need to find the black node, but we don't actually need to point to it. All we need to do is figure out whether it's on the left or the right. So, for instance, if green arrow left and green arrow right, and green arrow height, left arrow height is bigger than green arrow right arrow height, then then we know that black is to the left. So in this case we have a what's going on here? So green is equal to purple dot left. So a left dot left is a case 1. So remember, in case 1 we rotate right around green. So we rotate right, green. Else if green dot left and green dot right and other things. So let's do this way. If this, then we rotate. Else if, I guess else really, we have an issue because we have to rotate. So this is the let's just say what this is. This is the left case, which is case 1. This is left-right case, which is case 2. So we have to rotate around green arrow right, and then we have to rotate right around green. I guess we're rotating right around green in both cases. And then there's a whole bunch of other edge cases, right? Plus a ton of edge cases. And there's also the symmetric cases here. So there's just a huge amount of like symmetric cases going on. So for instance here, basically to finish this off and to finish off today, if both these are the case, we'll have to, but now this is left, so we have to rotate, I think, rotate left around green arrow right, and then we'll rotate right, or no, we'll have to, I'm sorry. I'll have to figure out whether I've done all this correctly. So that's right. But technically this is still incomplete because this assumes that both of the children are not null. If both of the children are, or if one of the children are null, then that basically tells us the direction we have to go in, and it tells us what case we have. But yeah, so there's like 2 more edge cases here, and I have really 2 more edge cases here, right? So I guess really we can just do it like if green arrow left, then we will just, this is still case 1, so then we rotate right around green, and then else if green arrow right. Now we're in case 2. And then the same things here. So copy, paste, right, left, 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 right, left. And so I think that actually finishes it. Isn't that horrible? A lot of times they make helper functions to do some of this stuff, but here it is in all of its glory. Either you go, this is basically all just figuring out which of the 4 cases we're in. If you're in case 1, then you rotate right. If you're in case 2, then you do left, right. If you're in case 3, then you do right, left. And if you're in case 4, you do left. I mean, it's drawing all this stuff is easy. The hard thing about all of this is just figuring out if anything is null or non-null or all that stuff, because basically the point is, like, if something is null, then you just have a huge amount of edge cases, right? Because, like, if one thing doesn't have a child, or green doesn't have a right child, or green doesn't have a left child, then you can't check its height, that kind of stuff. So, I mean, really, I guess we could shorten this if we actually make like a helper function, like a getHeight helper function. No, so all of this here is, so this is the fix-up code, right? So everything after this fixes it up. So what this does is it determines what case we're in, right? It tests to see if, basically you need to find out, here's purple. You need to find out if green is the right child or the left child. And so that's the first thing you have to do. And then you have to find out if the black node is the right child or the left child. Because remember, the structure of all of these rotations has to do with these nodes already being labeled for you, right? So green is P, grandparent is purple. And so if you already know these nodes, you don't have to do any of this. But if you don't know what these nodes are, then you have to find out which one is purple and which one is green and which one is black. And that tells you the structure, right? Because if the black one is on this side and not this side, then you have to figure that out. And so that's what all this code is doing. I'm going to post this all to the GitHub so you guys can look at it. We might fix this code up and make this a bit better. And I guess what I'll do is I'll test it out next time. We'll do some, and then we'll start red-black trees. We'll do red-black tree insertion next time. And I promise you I am not going to, so this is the simple implementation, okay? AVL is by far the simplest implementation. It's easiest to think about. It's not as bad. Red-black tree implementation, on the other hand, is like 3 or 4 times as bad, which is why I don't think they've ever asked for a red-black tree on any project, like ever. And the reason is because just imagine, just think about the problems that students would have. Just think, right? This is the easy implementation. Now, there are ways to make this better. And if you actually look at the pseudocode in a lot of the stuff like this, then like the pseudocode in the book is actually not so bad. It's kind of short. But on the other hand, the problem with that, the pseudocode, is that like it kind of, well, they do a lot of simplification. They use some helper functions. Well, I don't write the projects, right? So I would not recommend. So the thing is that, like, this is definitely in the easy case. So we don't want the hard case. I mean, I'm not even going to venture to implement the hard case in real time. I think you see that it took me the entire class to really do this. It would take me 4 hours to really implement a red-black tree. So, okay, cool. That was fun, right? We can implement everything else later. Yeah. All right. So there's an interesting fact about AVL trees that I do want to get to next time. Yeah, the course chair is Don Yai. So he's doing it. His project 1 wasn't so bad. So I mean, like, just cross your fingers for project 2. I think project 1 is okay. Project 2, who knows, right? So, okay. With that, I'm going to end the lecture. I want to talk a little bit, the things I want to discuss about AVL trees is things that you're not going to really do in the implementation. So I'm not going to do any more implementation for AVL. The one thing I would like to discuss next time is that the number of nodes in an AVL tree is bounded below by the Fibonacci numbers. So basically the number of nodes in an AVL tree is bigger than or equal to the fib of its height. And I think that is just pretty awesome. And so we'll do that proof next time. I think that's a cool proof. Yep. All right. Is that it? I think that might be it. For now. Okay, next time.